The moon so close to the Earth? Is this a figment of our imagination or something out of a sci-fi novel? Neither really. Countless years ago, during the evolution of the moon and the Earth, the moon was in fact this close to us. Over the years, due to tidal forces, the moon started receding at the rate of 3.8 centimeters every year. Today, at 384,000 kilometers away from the Earth, it is still the celestial object closest to us.
No one is certain how this charcoal black and snow white celestial companion of Earth was formed. The most likely theory is that a Mars-sized planetary body, traveling at high speed, collided with the young Earth. The molten material from the two bodies eventually formed the Moon. With relatively less gravitational force and due to lack of atmosphere, the Moon's surface has changed very little, preserving in itself the history of planetary evolution. Fascinated by many such facts about the Moon, humankind dreamt of reaching the Moon someday. This dream became a reality in the middle of the 20th century. In the 1970s, however, the focus shifted from our Moon, and other planets and their moons became the target of space missions. The interest in exploring the Moon was reignited in the 1990s when the space probes found evidence of what appeared to be signs of water ice hidden in shadowed craters in the Moon's polar regions. This initiated a renaissance in lunar exploration, of which Chandrayaan-1, India's first mission to Moon, is also an essential part. Chandrayaan-1 mission will fulfill the Indian dream of reaching the Moon. It is India's first mission to venture out beyond Earth's orbit and travel into deep space. Chandrayaan-1 spacecraft is cuboid in shape, of approximately 1.5 meter sides, weighing about 1,400 kilograms at launch, and will have a mass of 590 kilograms in lunar orbit. A three-axis stabilized spacecraft, its orientation control and high stability is ensured by its electronic brain, with the help of sun and star sensors, gyros, reaction wheels and propulsion system. Chandrayaan-1 spacecraft's propulsion system uses monomethyl hydrazine as fuel and mixed oxides of nitrogen as the oxidizer. Liquid apogee motor and thrusters are an essential part of the system. A single canted solar panel will generate a maximum of 700 watts of electrical power. During the eclipse period, the spacecraft will be powered by lithium-ion battery. ISRO Satellite Center, ISAC-ISRO's lead center for developing spacecraft technology, has designed and developed Chandrayaan-1.
The Chandrayaan-1 spacecraft carries 11 scientific instruments or payloads developed by the Indian Space Research Organization, the Physical Research Laboratory, and other scientific institutions from across the world.
Of the 11 payloads, 5 are indigenously developed in India. Terrain Mapping Camera (TMC) and Hyperspectral Imager (HiSi) developed by Space Applications Center, ISRO, Ahmedabad. High Energy X-ray Spectrometer, HEX, developed by Physical Research Laboratory, Ahmedabad, and ISRO Satellite Center, ISAC, ISRO, Bangalore. Lunar Laser Ranging Instrument, LLRI, developed by Laboratory for Electro-Optic Systems, LEOS, ISRO, Bangalore. Moon Impact Probe, MIP, developed by Vikram Sarabhai Space Center, ISRO, Thiruvananthapuram.
As part of international cooperation and an exchange of ideas, information and knowledge, ISRO announced an opportunity to all scientific institutions to fly instruments on Chandrayaan-1. Of the many proposals received, 6 were selected on the basis of scientific merit in meeting with mission objectives of Chandrayaan-1. Of these, 3 were from the European Space Agency ESA, 2 from American NASA, and 1 from Bulgaria.
The ESA payloads on board Chandrayaan-1 are Chandrayaan-1 Imaging X-ray Spectrometer 6 is jointly built by Rutherford Appleton Laboratory, UK, and ISRO Satellite Center, ISRO. Smart Near-Infrared Spectrometer SIR-2 is developed by Max Planck Institute for Solar System Science, Germany. Sub-kilovolt Atom Reflecting Analyzer, SARA, is a collaborative venture between Swedish Institute of Space Physics, Sweden, and Space Physics Laboratory, Vikram Sarabhai Space Center, ISRO. NASA-facilitated payloads are Mini Synthetic Aperture Radar, MINI-SAR, from Applied Physics Laboratory, Johns Hopkins University. Moon Mineralogy Mapper, M3, from Brown University and Jet Propulsion Laboratory. Radiation Dose Monitor, RADOM, is the 6th payload from abroad being accommodated on Chandrayaan-1. Chandrayaan-1, with the support of all its 11 onboard payloads, will systematically map the entire lunar surface, investigate the Moon's mineral and chemical composition, detect water ice, if any, on the lunar surface, and through all this, look for clues on the origin and evolution of Moon.
Amongst the challenges confronting ISRO, the foremost was reaching the Moon. The Polar Satellite Launch Vehicle, PSLV, was selected for this as it inspired confidence amongst Indian scientists and scientists across the world. The PSLV XL, a newer and more powerful version of PSLV, has been employed to launch Chandrayaan-1.
The complete design and development of PSLV XL is done by Vikram Sarabhai Space Center, Thiruvananthapuram. ISRO Inertial System Unit, IISU, Thiruvananthapuram, has contributed all the critical devices needed for controlling vehicles like gyroscope and navigational system of the launch vehicle. Liquid Propulsion System Center, LPSC Thiruvananthapuram, has indigenously developed the liquid propulsion system and provided the liquid propulsion for the vehicle. The solid propulsion system and engine used at stage 1 and 2 is developed by Satish Dhawan Space Center, Shar. Total assembly of the vehicle and all launch-related activities will be coordinated by SDSC Shar. The 44-meter tall PSLV XL has 6 strap-ons with solid engine at the first stage of separation, liquid engine Vikas at the second stage, again a solid engine at third stage, followed by a liquid engine at the fourth and the final stage of separation. PSLV-XL will inject Chandrayaan-1 into an elliptical transfer orbit ETO, measuring 250 kilometers perigee and 22,000 kilometers apogee. PSLV will inject the Chandrayaan into this orbit at a velocity of 9.89 kilometers per second. From here on, all the post-launch operations will be coordinated by ISRO Telemetry, Tracking and Command Network, ISTRAC, Bangalore. The existing network of ISTRAC ground stations, along with support from foreign agencies, will track and communicate with Chandrayaan-1 during its journey towards the Moon. The orbital period of the spacecraft in ETO-1 is 6.5 hours. The spacecraft circles the Earth for 3 to 4 times in the same orbit. The LAM is fired near perigee, which increases the apogee to 40,000 kilometers and enables Chandrayaan-1 to go into the second extended transfer orbit, ETO-2. The orbital period of the spacecraft increases to 18 hours. After the second LAM firing, Chandrayaan-1 will go to the third extended transfer orbit, ETO-3, increasing the apogee to 70,000 kilometers. The orbital period will be 24 hours. Chandrayaan-1 will be put into an elliptical orbit where the apogee will match with the distance of Moon from Earth. Satellite will take 11 days to complete one revolution in this orbit. During subsequent revolution, the trajectory correction for approach to Moon will be carried out. Beyond the 100,000 kilometers, the ground stations of the Deep Space Network will provide support to the mission. From here, the spacecraft will coast along for about 5.5 days before it reaches the vicinity of the Moon. The newly established Indian Deep Space Network, having 18 and 32 meter antennae at Bailalu near Bangalore, is a very unique facility, having several critical technologies established for the first time in the country. The 32-meter antenna and the associated electronic equipment have been designed and developed for ISRO by Electronic Corporation of India Limited, ECIL. ISRO Satellite Center supplied the feed subsystem. On-site installation and commissioning are executed by ISRO Telemetry and Tracking Command Center, ISTRAC. Operating in S and X bands, the 32-meter antenna is capable of receiving extremely weak signals from the spacecraft, which are millions of kilometers away from Earth in deep space, and can also send very strong signals to the spacecraft. An 18-meter diameter antenna working in S and X bands will also support the mission. The Indian Deep Space Network antennae can be operated remotely from ISTRAC Network Control Center at Bangalore through a monitoring and control system. As Chandrayaan-1 spacecraft travels into deep space, mid-course corrections will be carried out as and when required. When the spacecraft is about 500 kilometers from the lunar surface, a major maneuver called Lunar Orbit Insertion, LOI, is performed. Chandrayaan-1 will achieve its final Moon orbit 20 days after the launch. After this, Chandrayaan-1 will enter into an elliptical orbit around the Moon, with the nearest point being about 500 kilometers from the lunar surface and farthest point being about 5,000 kilometers. After the subsequent health checks, the spacecraft's orbital height is planned to be lowered through a series of planned maneuvers to achieve the target altitude of 100-kilometer circular polar orbit over the surface of the Moon.
After reaching operational polar orbit, the payloads will be commissioned one by one. The first to be commissioned is the Moon Impact Probe, MIP, a technology demonstrator. It will be released at the